Okay, so this is a review of section 3.1, ionic and covalent bonds. So we're going to begin with the question, why do atoms bond? The main reason is what we call the second law of thermodynamics. The second law of thermodynamics basically says that all systems tend to move to a lower energy state. So for example, if you stack blocks on top of each other, you're increasing the energy in the system, which is the stack of blocks, as you stack them higher and higher. You usually tend to get to a point where the stack becomes unstable. It's too high energy. It starts to wobble. And even if you stack the blocks as carefully as you possibly can, the blocks get to a point where they will just simply fall over. There's a limit to how much energy you can put into the system. So then the blocks fall over, and all of that extra energy in there is transformed into kinetic energy as the blocks fall, which is then transformed into friction or heat energy when the blocks strike the surface, and a little bit of sound energy because the blocks usually make some amount of noise. So that it goes to a lower energy state. So what does that look like for an atom? Well, in order to determine that, we look at atoms that are already atoms that don't bond. Atoms that don't bond. Because it stands to reason, if an atom won't bond to another atom, it's because it's already in the lowest energy state possible. So the answer there is the noble gases. Well, what's special about the noble gases? Well, if we look at their electron configuration, they have filled S and P orbitals. So for example, neon. And if I do the shorthand for neon, that would be helium, 2s2, 2p6. Okay? So it's S is full of 2, that's the maximum S can hold, and the p orbitals have 6, that's the maximum the p orbitals can hold. So what does that mean for the other atoms? So in order for an atom to get to a low energy state, in other words, how does an atom get full s and p orbitals? Okay. So atoms are going to do a couple of different things. There's a couple of different options. They'll give, take, or share electrons to have full s and p orbitals. Okay. and it's going to share the valence, do giving, taking, or sharing will be the valence electrons. These are the electrons in the highest energy level. So how do we know how many electrons or what electrons are called the valence electrons for any particular atom? Well, if we look back up here at neon, we can see that neon has electrons in the 1s, that's the helium represented here, and it has electrons in level 2, and those are the 2 s orbitals and the 2 p orbitals. Those are in the highest energy level. So these right here, these 2 are valence electrons, and these 6 are also valence electrons. So neon has 8 valence electrons. So happens that the atoms have, the families that we learned about in our last unit, have a pattern as to how many valence electrons each family has. So for example, if we look at sodium is neon 3s1. That's the shorthand configuration for sodium. So these are all the electrons in the 1 and 2 energy level, and this is one in the 3rd energy level, and there's only 1 in the 3rd energy level. So this has 1 valence electron. So let's take a look here. Get out your periodic tables if you haven't done so already, and we're going to mark up our periodic tables. We're going to write by family how many valence electrons are in each of the different families. Okay, so we're going to start over here with the alkali metal family, and while hydrogen is not a member of the family, we're going to include hydrogen in our pattern. Okay, we just said that sodium has 1 valence electron. That means that every member of this particular family also has 1 valence electron. I'll make that so it definitely looks like a 1. Okay, the next family here is the alkali earth metal family. So for example, magnesium here has an electron configuration of neon 3s2. So in this case, level 3 is the highest level with any electrons in it, and there are 2 electrons. So magnesium has 2 valence electrons, which means that every member of the alkali earth metal family has 2 valence electrons. Okay, now we're going to skip the transition metals. Okay, and we're going to go over here to the boron family. Okay, so if we look at aluminum, aluminum is 3s2, 3p1. So it has, in level 3, 2 electrons in s and 1 electron in p for a grand total of 3 valence electrons. You noticing a pattern yet? Okay, we go to the carbon family. Okay, so now, okay, if you look at here, we look at silicon. Silicon would be 3s2, 3p2. So there would be 2 in the s and 2 in the p. So this family has 4 valence electrons. Okay, so the pattern, it keeps going up in steps of 1 as you go family by family. Okay, so we're going to go back up here for a minute, and we just said that atoms are going to give, take, or share electrons, in this case they're valence electrons, in order to fill up their s and p orbitals. So which atoms give, which atoms take, which atoms share. Let's go back to our periodic table. Alright, so we have elements with few valence electrons on this side, and elements with a lot of valence electrons on this side. Okay, now before we go on, we're going to fill in what's going on with here, and we're going to make a little funny note here. We're going to put here the number of valence electrons varies, means it's changeable. Okay. So we're going to come and talk about these later in the unit when we start talking about nomenclature. Okay, and we're going to do the same thing down here. So make sure that you've got your periodic table nicely labeled by family with the number of valence electrons. Now, we're not going to actually talk about these for a little bit. We very, very, very seldom see compounds. We see some, but we don't see a whole lot of compounds that are formed by the intertransition metals. There's a lot of compounds that are formed by the transition metals here, but they're going to do something a little bit different than some of the elements in these families and these families. Okay, so if I drew the stair-step line, which you should have on your periodic table, if you don't have already, get a big thick marker and draw it in. Okay, remember, this line, called the stair-step line, divides the metals from the non-metals. Okay, remember that hydrogen is a non-metal. Okay, so on the left side, these are all the metals, and if you notice, the metals have 1, 2, or 3. Now we're looking at the ones under here. Maybe up as high as 4 valence electrons. Now the non-metals here tend to have 4, 5, 6, 7, or 8. So we can say the metals don't have many valence electrons, and non-metals have a lot.